This is 2.6, Limits at Infinity and Horizontal Asymptotes, Content Objective 2, which is to find limits at plus or minus infinity using growth rates and end behavior models of functions. By the time we're done, you should be able to write what you need to do with a function that has more than one term before you can compute its non-infinite limit. So, for example 1, we want to use end behavior models and growth rates to determine the following limits. So if I look here, I'm going to eliminate all but the dominant terms on both the top and the bottom. This one, since there's only one term on the top and only one term on the bottom, I can just compute the limit. What happens to 1 divided by x when x gets really, really large? That's like having 1 grain of rice split among 1 trillion people. Essentially, each person gets nothing. So the limit for this one will just be 0. If we look at this one, now it's a little more complicated because we have more than one term on both the top and the bottom. So at this one, we will look and see that we have polynomial terms and that the cubic is going to outpace the linear and the constant. Same thing on the bottom, that 2x cubed is going to outpace the x and the negative 1. So the dominant terms for both the top and the bottom, or the end behavior model as x goes out toward infinity on the top, will be just 4x cubed, and on the bottom it will be just 2x cubed. So if I reduce that, I can cancel the x cubes, cancel the 4 and the 2, and end up with an answer of 2. If we look at this one, we want the limit as x goes to infinity, so again we are looking for the dominant terms. On the top I have an x. There's only one term, so that one's going to be pretty easy. On the bottom, it's a little bit more complicated. So we have to think about how x squared dominates over the 1, and the square root of x squared when x is positive will just be x. So if I reduce those two, I end up with a 1. Now with this one, notice I tell you to be careful because I want x to go to negative infinity as opposed to positive infinity. The top is still going to be dominated by that same linear term x, but on the bottom, when we look at this x squared and we take the square root of it, we do not get x. We actually get something different. So what I'm going to do is I'm going to have you look at the square root of x squared on a graph. Here's that square root of x squared, and it looks an awful lot like something else. Hopefully you will recognize that as the absolute value function. So we have, as the limit as x goes to infinity, negative of x over the opposite of x, because as x becomes negative, more and more negative, this function will strip it of its sign and make it positive by multiplying by a negative 1. So in this case, our limit will be negative 1. To illustrate that, I want you to look at this function, which is the original one, x over the square root of x squared plus 1. And you can see that on the right-hand side, those y values are getting closer and closer to a positive 1, whereas on the left-hand side, those y values are getting closer and closer to negative 1. Next, we have some new notation, and this notation will be used to illustrate or communicate that a function is becoming unbounded. So we've seen it a little bit before. On the right side, we've said that limits approach infinity, but we have not seen them while x is also approaching infinity. So if we read this notation, it says the y-coordinates are getting larger and larger and larger as x moves further and further to the right. So what this means is that for any positive number I can choose, there's going to be another positive number that if x gets bigger than n, then the outputs are going to be bigger than m. So no matter how large I choose that, I can always surpass it if I go far enough right on the graph. So if we want to use end behavior models and growth rates to determine these limits, we can think about what happens on that growing side of the exponential as x gets bigger and bigger. Well, we end up with infinity. Just gets bigger and bigger. This one, we have the limit as x approaches negative infinity on e to the x. So notice on this one, instead of traveling to the right, we're traveling to the left. So the y-coordinate on that one is going to be 0. On this one, we now need to evaluate dominant terms. So on the top, there's just one term, so it will dominate. But on the bottom, we have multiple terms. So we're going to take the dominant one, which is a 4x to the 8th. Now what we're going to do is we're going to think about which of these grows faster using the n to the n FEPL. The n FEPL. So here I've got an exponential on the growing side divided by a polynomial. The exponential is going to get much larger, much faster. So that means the numerator is going to be much larger than the denominator. When that happens, we end up becoming more and more unbounded. We get larger and larger. Next one, we have x is approaching positive infinity. So on the right-hand side, that absolute value of x is going to leave things alone. And on the bottom, the dominant term will be a 3x to the 5th. So now we are comparing a logarithm to a polynomial. And in this case, the polynomial outpaces the log, because polynomials come before logs in our acronym. So this 3x to the 5th is going to dominate over the log natural, so we'll have relatively small numbers divided by large numbers. That's going to get us closer and closer to 0. For our final example, I want to compute the limit as x goes to infinity on this expression. So don't write this yet. Put your pencils down and just listen for a minute. Most people, when they are examining this limit, they want to again think about dominant terms. And they say, okay, well, I'm going to let the limit go to infinity. And the dominant term here is that square root of x squared minus the dominant term here is just an x. Now this one is, if we recall from the problem we just did, that's the same as the absolute value of x. And since x is going to positive infinity, that means the insides of this will be positive. So I'd end up with an x left alone minus an x, which gives me 0. So most people will follow that logic and think they have the right answer, and then they might go to their calculators or to their graphs to double check. So we're going to go look at that. Let me get it up. Okay, if we look here at this picture, you can see that I've graphed y equals the square root of x squared plus x plus 1 minus x, and we can see that we don't really seem to be getting close to 0. Instead, we seem to be getting close to something else. So maybe we just haven't gone out far enough. Let's go out a little further, say maybe to 250, and we still aren't really getting close to 0. Let's go out to 1,000. We are not getting closer and closer to 0. Instead, we seem to be stuck right along this value, and it appears to be about 1/2. If I go back to it so I can kind of see my scaling on my y-axis, it looks like it's at about 1/2 here. So what is going on? Where does that 1/2 come from? Well, if we go back to our notes here, we can erase the reasoning that I used before. So hopefully you didn't write that down anyway because you were just listening. And what we're going to do now is we're going to think about this in terms of how we did these ones. In these two here and in the ones that came in example 1, we could only identify those dominant terms and work with them when we had fractions, because we were comparing end behavior models of the top with end behavior models of the bottom. And in this one, we don't have a fraction. So what we're going to do in order to work with this is we are going to create a fraction, and then we're going to make a smart choice for 1 so that we actually get something that we can compare the growth of on the top and on the bottom. So if I multiply by the conjugate, which is typically what we do when we have square roots involved, then we can see that on top we will have the inside of that root minus the x squared, and on the bottom we will have the root minus the x. Now if we look at dominant terms, we will have an x squared minus an x squared. Those will cancel, and I'm left with the dominant term, which is an x on the top. And I can treat this x squared as absolute value of x, which has positive insides. We'll be leaving that x alone, plus, sorry, I multiplied by plus another x. So I'll end up with a limit as x approaches infinity of an x over 2x. The x's will cancel, and I'll end up with a half. And there's that half that we were seeing on our picture that we appear to be getting close to. So based on the examples that we've done above, we should be able to talk about what happens when we have a fraction and the bottom grows faster or has a dominant term. When the bottom's growing faster than the top, then we're going to approach 0 as our limit. If, on the other hand, the top grows faster, then depending on whether the top is getting bigger in the positive direction or its magnitude is getting larger in the negative direction, we will have the top dominating over the bottom. And lastly, if f and x grow at the same rate, then we will end up with something that is a constant not equal to 0. So I'd like you now to do your notes web exam problems through number 8, and then based on these, write down what you need to do to a function that has more than one term before you can compute its non-infinite limit.